Welcome and good morning for the 12th session for type systems for correctness and security. Today we're going to talk about Scala's type system. This is also going to be the last lecture of this semester. We will continue in the following weeks with some discussions on exercises, of course. And of course, don't forget today's office hour at 2. By the way, I have to postpone this to 2:30 today because I have another appointment at 2. I will write that in Panda as well. Good. As usual, we will start with the exercise. Get that clear for you. And And in this exercise, we were talking about security type systems. So things we talked about for securing programming languages. Good. So the first exercise was basically a bunch of derivations to do. So let's quickly walk you through these. So the rules from slide 25 to 28, we would like to be able to type check these programs. Okay, let's do this. Good, so the first one was H assigned L plus 4 sequenced with L minus 5. And of course this whole thing has a context. We just don't know what it is yet, low or high. Let's see what we have. Good. So let's go one place up. Because it's a sequencing, we have kind of to derive two things here. And let's start with the right one, because this seems to be rather easy. So let's try it out and say, okay, what is this? And low is assigned to low minus 5. That can be done when low minus 5. How do we type that? Obviously as low, because there's no high. And we can do this because H is not in the vars, the variables of L minus 5. In this expression there is no H, so we can do that. And of course all of this is in the low context, so this happens to be type checking really well. So what about the left one? It's H L plus 4. What is this? Well, L plus 4, we can do basically the same here. L plus 4 is also low because H is not in the variables of L plus 4. You see? And of course all of this is also typed as low. It like has a low context because we did not access any high variables here. Good. Let's move on to the next one right away. That was if H equals 1, then H is assigned to H plus 4, else skip. What about this one? Okay, well, from the skip rule, we can already see that regardless of whatever we find, we can always execute a skip, and this is true as an axiom, because skip is always possible in any context. Okay. And then we will see, okay, this can be typed in any context, however we would like that to be, and the condition here H is 1 is of course high. This is a little bit different than I did it in the solution. It's just taking one step more here, saying okay, the condition is high because it reads the condition. It's an equal operation with the high. So this is typed as high, and the expression here is also in the high context, because it's h plus 4, we're reading h again. And you can pretty much figure that out for yourself. It's pretty easy from this way up to do so. And this puts all of this, of course, in the high context, because we're reading from high, and this is the condition of high. So the whole thing must be high, especially when the condition is here. In the solution, I just wrote PC here. This means that we can we have to fill in all the same here, and as the condition is high, PC needs to be high, and it pushes it throughout, so this PC is also high. Good. So the third one is a very short one. It's L assigned to H, H assigned to L in this case, and then a skip. Good. In order to make this work, it's an assignment too low. Remember, this is assignment too low, and assignments too low must be in the low context. And then you have skip, which is in the same context as the left one. And of course, this would push things down here also. However, you cannot show this, because you cannot ever assign something too low, which is in the high context. So this won't work. Okay, next one. Oh, it's still on there. That's good. So that was 1, 2, 3. No, wait, 4. Okay. So let's be rather pessimistic here. Start with just PC. So this is the target context, and it's if h equals 1, then L is assigned to 12, else skip. So your intuition always already tells you, oh hey, we have an observation on low. We can observe make an observation on this low variable here, depending on this high context. This should not be possible, but let's find out how this works. Okay, let's start again with a skip, because it's so easy. So this holds whatever. Then we would like to type the condition, and the only way how we can type that is as high. And the only way we can type this assignment here is in the low context, which means that this would be 12, and if we then check if 12 would be in the low context, it isn't, because we have to consider the condition context here, which is a high, and these two things contradict each other. So we cannot type this. Okay. I'll have to scroll you in again. Okay, this is expression number 5, and expression number 5 says that's a little bit more complex. Okay, let's start conservatively again with a PC here. So this is the current context, and it's if h equals to 1, then L is assigned 12, else skip. So this is the same thing as we had before. However, L is then overwritten with 42. And the idea here is to check if this is still, if this could still be typed, or if we still have a problem like we did before. And of course we can still, we can still start with the right one and say, okay, this is PCL42. However, we would then have here that there would be typing context PC on the left one as well that could type this again. Let's skip. So this can be done somehow. The problem is we already know that we cannot do this because we have a condition here that is in the high context, and we have an assignment that must be in low context. Oops, no, this is it. And in the low context, and of course you can always do the skip, but that doesn't help you. So you again, as in 4, have this little problem that this and this is contradicting each other, and this won't type check. Okay, let's go for the next one. So for this we said, okay, there is a while loop, and while L is bigger than 4, do L minus 1, H plus 1, skip. So we have a low condition, we have a low assignment, we have a high assignment, and a skip. So does this work? Let's find out. Let's first type the while loop, of course. And for this, we need to establish that L bigger than 4 is low. And the way we do this is we say that H is not included in the variables of L bigger than 4, which is obvious. And then we need to type the body. And I'll leave the context open for a second now here, so you can see what's happening. We say L minus 1, and of course this is an assignment. H plus 1, skip. So how can we type check that body? Well, let's start with the first part on the left here, because we're like it's a sequence, and then we unroll from the left first, and there we say that, okay, we have an assignment here to low, so this must be in the low context. And so it's L is assigned to L minus 1. Remember, low assignments need to be in the low context. And this can happen when L minus L is in low. And we can show this by saying, okay, H is not in the variables of L minus 1. Okay. So as we now establish that we have to be in the low context because we have a low assignment, we push this down here, and we also push this down here, and hope that we don't have a contradiction on the right side. So the idea now is that we type all of this in the low context and hope for the best. So this is the right part of the sequencing, which is a sequence itself. So we can decompose and we can say, okay, low h equals h plus 1, which we can do because we don't have any, we can type high assignments in the low context. That's possible. When we are in the low context, we can make assignments to high, unless we are kind of forced to be in a high context, as we've seen in the if. So the problem was that we had a low assignment here that pushes us in the low context. However, we need to be in the high we need this to be in the high context, and this is contradicting here. Here it's quite the same, so we can do this, and of course we can type the thing, the skip in the low context, and this now works. So we're pretty much set on all of these. So this type checks pretty good. So in essence, 3, 4, 5, 3, 4, and 5 did not type check. 1, 2, and 6 did type check very well. Okay. Questions for the first part for 10.1. Gives me an opportunity to drink coffee. Okay, doesn't seem to be the case, so we'll go on a little bit to 10.2. And in 10.2 we were talking about lattice-based security. So the exercise had a little bit of an introduction. So in a lattice-based security type system, there are more than one security levels, just not high and low, but multiple, that are organized in a partial order. So we have this lattice, for instance. So this lattice gives us the relationships between the between all of these security levels. And the question now was that given this lattice, would the following programs type checks? And for this we use the Volpano and Smith rules from slide 32 and following. Okay. So number 1, and writing down derivation trees always is a little bit of a hassle because I hope I have enough space in the top. So first thing that I do is it's a little bit lengthy, so the context is a little bit lengthy, so let's write it down first. So this is the context in the first exercise that needs to be considered. So A is of type X and B, or security level X, and B is of security level X and Y. Good. And so the thing we needed to type check is under the assumptions of gamma 1, this one, does it hold that if A equals 0, then B is assigned 12, else B is assigned 1, and this all needs to be typed. So what is the outcome type of this? Okay. And how we would do this is, of course, we use the if rule and decompose the if. So we have gamma 1 says A equals 0 is of type X. And then we have gamma 1 that says B is assigned 12 is assigned to B. And this, of course, because it is XY and is an assignment, needs to be XY CMD. And also we have the third one here, the other condition here that helps us to say B1. No, B, there's no B1. B is assigned 1. This is the way. And of course, this also must be XY CMD. Yeah? This means all the branches are XY CMD. We have established that, so we can write down here XY CMD. And in the solution I just saw there is a parenthesis too much given in the LaTeX. But we have another condition that says that X must be in the partial order lower or equal X and Y. And this is not given. Because X is actually higher up in the lattice. If we scroll that up again, you can see that it's higher up. So this wouldn't work. So this condition is actually breaking the type checking for this. Okay, let's move on to number 2. So what's the context of number 2? It is B, XY, and C, XY, Z. This is the context in the second exercise. And the thing you would like to type check is if we can, under the assumptions of gamma 2, type check B, so assignment from C to B, and then a skip that needs to type check. Okay, how does this work? Let's start with the left part because it's the more complex thing and we know that we can do this all of the time. So under the assumptions of gamma B, so we have decomposed this sequence now. C is assigned to B, and as B is XY, this needs to be in XY CMD. Yeah, you see? Okay, does this type check? Well, in order for this assignment to type check, we need that gamma 2 at place B needs to be XY. So I literally took this a little bit too early here. Of course I needed to have some proof for that. And gamma 2C must be X, Y, and Z. Well, that's something that we can establish from here. And then we can see that X, Y, Z is below equal X, Y. And this holds because it is actually below. You can see in the lattice. And of course, always we can type the skip and we're done. So this thing doesn't type check, but this thing does. So rule of thumb, how is the third one going? Maybe a fail again. Let's find out. So as you see, the context under which we type this is the same as in the part number 2, so we can freely reuse gamma 2 here, which is neat. But does it type check? So let's find out. Gamma 2 C is assigned to B is assigned to C. So the opposite then from before, and we had a skip. Let's start on the first part. So we can always type this skip no matter what. This is interesting and good. And gamma 2 is then following the same principle, but now it's B assigned to C, so it needs to be X, Y, Z CMD, which means that we have to establish that C in gamma 2 is X, Y, and Z. This is fine. And gamma 2, we need to have a well-typed B with X and Y as its type. And then we would need to establish that XY is underneath XYZ. And that's something we cannot do. So this is where this type derivation breaks. So number 3 breaks again. Okay, let's go ahead. Number 4. Number 4 has a new context, and let's call it gamma 4, of course. And this thing has the empty type label for D. E would be X, Y, Z, and F would be Z. This would be that. Okay. Then we would need to establish under the assumptions of gamma 4, if D equals 12, then E would be 42, and else F would be 23. And as you can see, this is an interplay of the condition level and the output levels. Of course, the output levels also don't match, but also the condition level does not match. So it's not a trivial case. So let's find out if this works. Let's decompose. So under the assumptions of gamma 4, D12 has the empty type, and under the assumptions for E42, E assigned to 42, has X, Y, and Z as its type, but as a command, because we're now assigning. And then under the assumptions of gamma 4, F is assigned 23. And this is Z command. Now, how do all of these need to be in a relation? Well, the condition type must be lower equal X, Y, and Z, and also needs to be lower than Z. And is this the case? Let's scroll up to the lattice again. It is not. The empty type is actually on the top. So this fails. So this does not work, and so the entire type check fails. So it's basically the same mechanics as we had in the high-low context, but just to compare high and low, we made it more complex with this partial order here that is given by the lattice on the exercise, and we need to check if types are compatible or not. Okay, more questions towards 10.2. Okay, then let's move on. So 10.3 had this nice little Java-like language that we also looked a little bit at. So there is this following class. So C in the context of L extends D. And we have two booleans, F in the high context and G in the low context. And then we have a function called do something that takes a low boolean and a high boolean, so X and Y, and has a heap effect of L according to the definition. And then let's see if this is actually true. So we have if X, then F equals this dot F equals not X. So this is an assignment to a high from a low, should be fine. Conditioned with the low should also be fine. And else F is X. So in F is depending negatively. It's always the same, more or less. It's always false. And then we have this dot G, which is a low boolean depending on high parameter. And then we have the return. This is a comparison of X, a low boolean, with G, also a low boolean. Then we had a lattice given. And the lattice is rather easy. We just have low and high. And now the first part of this exercise was what would be the type of the method do something. So the type for this, how do we determine this? Well, of course, in the left part of the function type, there are the parameter types, and which is X, which is boolean low, and we have Y, this is boolean high, and the return type is actually denoted here, which is boolean high. And then the heap effect of that is denoted after the function signature, or it's part of the last part of the function signature, and this should be L in this case. So I'm just taking the parts of the definition and writing the function type down here. Okay. The next question was, would the class type check in its current form? If yes, give a usage context where typing may type check. Would the task type, if yes, give a usage context where the typing context may fail? If no, what would you need to change to make it type check? Usage context where it fails. Okay, now I get it. Okay, the thing with that is it will actually not type check. I'm scrolling up to the code again, to the function body, to make this argument a little bit more visible. So there is an assignment to G, and as we've seen here, no, you don't, I do. G is low, but we assign it the parameter Y, and Y is in the high context. This would violate type safety, as we would as we would then assign something to a low variable from a high context. This would not work. And the return value is derived from this .g, which is on the low level, but this can also be typed as high. So this is fine. So we have two critical parts here. The first critical part was that this .g is assigned to y. And this part is defined in L, and this part is defined in H. And as we know from non-interference, like a high context should never influence a low context, this actually is not good. And then again, we have another usage of this .g in the return. So x equal this .g. So we established that this should be L, and this is also L from the function definition. To push this up a little bit. And this is all fine. So this would be typed as low, the Boolean that comes out here. So this is also a Boolean L, but we can always lift things to the high context, and then we're good to go. So this usage of key is problematic, and this actually fails to type check. However, the second use, this is actually okay. And this is what we see here. Good. More questions to this Java-like exercise part 10.3 maybe. Okay, seems to be a quiet morning, so let's take 10 minutes until 10:50, and then we'll start with the lecture.
Tirado en el ataúd, este cementerio no se viene a descansar. Salimos de la tumba al caer la luz y todos los cadáveres empiezan a bailar en el guateque. El guateque de los muertos. Es el guateque de los muertos. Satán está pinchando el rock del infierno. Tres calaveras dicen cha cha cha. Los descuartizados mueven los pies. Aquí solo está muerto el que no sale a bailar en el guateque. El guateque de los muertos. Es el guateque de los muertos. Satán está pinchando rock and roll en el averno. El guateque de los muertos. Es el guateque de los muertos. Satán está pinchando rock and roll en el infierno. cómprate algo de tu talla y únete al Bim Bim Badaboo, que han vendido el pantalón roto. Estás francamente de poder. A la cárcel por llevar hombreras, a la hoguera esa riñonera. Ponte un gorro elegante como los de antes, a juego con tus tirantes. Ponte un gorro elegante como los de antes, a juego con tus tirantes. Ponte un gorro elegante como los de antes, a juego con tus tirantes. Que te pongas un gorro elegante, gabardina y traje de tweed como los de antes, a juego, o sea que combine, que pegue, que quede bien con tus tirantes.
And so welcome back to the lecture for type systems for correctness and security. As I said, this will be the last lecture of the season. Today's lecture is supposed to be a little bit more light, as we won't do any proofs, but we will look into a practical type system today, and we're talking about Scala today. So you've been using Scala throughout the entire course, so you should be rather familiar with all of the things that the language has to offer. However, I would like to give you a little bit more insight on what you can do more with Scala's type system and what features it holds, and we're going to try out a few practical things today, so keep all your fingers crossed that my demos will work today. We will see. Good, so the first feature that you already have kind of found is that Scala has local type inference. So meaning that it considers like one expression at a time. So we have a few expressions here, and whenever the expressions are typed, these are typed in the specific moment that we do them. So in this case, we have we can actually write an identity operator that actually preserves the return type without stating it explicitly. And I would like to show you this a little bit besides here. And for this, of course, we need to have a Scala REPL. Could have prepared this, but now it loads, so you have the proper load time also. Okay, there we go. This took a little bit longer than in my demos. So what do we have here? So let's first define an identity function. We can actually do this here on the fly, can say, okay, let's take an identity function that is depending on a type t, that takes an argument of type t and returns x. You've seen I have not given it the explicit return type for this. So we can now find out if Scala actually determines that this is the identity function and it returns the same type as it has received. And it actually has. And as you can see now, not only is the input parameter typed as t, but so is the whole function. And this is type inference actually in practice in Scala. This is quite neat. Good. So what else can we do with that? So the first thing that we can always do in the Scala REPL is check the type. And now we would like to check the type out for ID. So there is a very basic version that gives you basically the type. So this is kind of the type parameter that we have, and the parameter of this type and the return type, as you can see. But we can also make it a little bit more verbose, and then you see the whole type signature and then the internal type structure. So this is the internal type that the Scala compiler actually stores the type. So you have a polytype, we'll get into that, what that is in a second, and you have a type parameter which is a list of type parameters t. You can have more than one type parameter, this is why this is a list. And then you have a return type, which is a method type, as you can see, with parameters of term symbol xt, and the return type of type param, type ref, type param t. And you can see this pretty much is comparable to the things you did in the labs. So let's try to find out. Let's use ID on 42 and see what it does. And it returns an integer, which is 42. And if I type this expression, you can type here any kind of expression. I can see this is an int. Does it only work with int? Of course not. We can also do true, and we can also do the things from the slide, which is ID Scala, which is a string, and then it returns a string. So this is pretty neat. So we can actually do the things that we had in the lecture, applied in this language. So this is local type inferencing for you in Scala. This is a pretty neat feature. And this has something to do with ascriptions. So it actually interacts with ascriptions in Scala. So you can do things like this. So you can define a trait. So a trait is just something you can mix in. It can have functionality. It does not have to be have functionality. I'm sure you've seen this in the solutions, at least in my labs, but maybe you've used this as well too. And you can define a function that gets something that creates a new something from this trait, and then you have something inferred, and then you have an explicit something. So let's try this out a little bit in the Scala REPL to see what happens there. So also in the Scala REPL I can start defining something, in this case the trait. And how was it? Okay, I want to have a function called get something that is a constructor call to new something empty, and this is something. We can see that, and we can of course infer this. And then we have something anonymous, and it's typed as something. But also we can make this explicit. We don't need to rely on the type inference to do something. I shouldn't have named it something. and we come to the same conclusion. This is not surprising, but interesting that either way we come to the same conclusion here. Oh, it's rather nice. So the type inference is pretty nice to us to infer this type, so we don't need to ascribe it anywhere we use it. We can explicitly ascribe it, and sometimes it helps the compiler to find matches a little bit earlier, especially in case, so you've all had the case in the labs where you needed to find the least common supertype for something, so the join, and maybe also a meet from the other direction. And this is typically where the compiler or the type checker in the compiler may come to a non-optimal solution, and you can help with description a little bit there. The other interesting thing is that we have a unified type system in Scala. So there is a type any, and there's also a type anyval, which is the supertype of any value object, and any-ref, which is the supertype of any reference object. And then you have nothing and null, and nothing is the bottom type for everything here. So in any case, any type you create and any type you use in Scala always has a least common supertype or subtype, which is at least any or nothing. Any meaning it can assume any type, and nothing can does mean it does not assume any type at all. Parameterized types. You may have seen this, and you know this a little bit from Scala, from generics. So you can have classes that depend on type parameters, and these type parameters can then be used inside of the elements of the class. So in this case, we have a stack, and this stack has a variable called elements, so it's the elements of the stack, which is then implemented as a list of this particular type, and is started with the null element. So it's an empty list. And whenever we push things to the stack, we add them to the list. When we see the top of the stack, we take the head of the list, and when we pop things, we just take the tail and disregard the head. So it's just a mapper basically between a stack and a list. The interesting thing here with parameterized types is you can add bounds, and you can add variance constraints to the type parameters. Do I have a slide for that? Yes. So bounds and type parameters give you that you can have upper bounds and lower bounds. You can have both, by the way. So you can say, okay, this list container is defined on a type, and this type is at least a list. So it has an upper type bound. And it also has a lower type bound, which means it is a supertype of bit set. So it needs to be in the bit set inheritance tree at some point. And as you've seen before, Scala has a unified type system, so all parameters have an upper bound of any and an implicit lower bound of nothing. And you can make that much more narrow if you like. So you can really limit your type parameters to the explicit parts that you would like them to be. And this is really, really neat in some situations where you want that feature to be really, really narrow and really defined on something. Also, once you provided these bounds, you can rely on them. You can say, okay, we have a subtype of list here, so this means that we can use all methods a list can use on this type, which is pretty neat. Variance in type parameters, pretty interesting. I mentioned this before when we talked about covariance and contravariance in this lecture, but in Scala you can actually use it. So let's say you have a class or a trait called tool, and you have a subclass called hammer. And then you can define a box which is covariant. That means any box of tool is also a supertype of any box of hammer. This can be really useful for function arguments, for instance. You can also make them contravariant and say any box of tool is a subclass of any box of hammer. So it goes into the opposite direction as the original class goes. We've seen applications for this before, why this can be useful to bound things in a certain way. And of course, you can always make things invariant and saying like, okay, there is no subtyping relationships between these two boxes, box types of box tool and box hammer. And depending on your use case, this one of these three makes total sense and the others don't. You just have to figure this out, what makes the most sense in your design. What's the semantics of your types. And by the way, the invariant case is the default case, so whenever you don't specify anything, it's always invariant, because it's the safe assumption. So let's look at covariance a little bit. So this is a little piece of code here. So you have a trait called animal, a class called mammal, which extends animal, and a class called zebra, which extends mammal. So kind of an inheritance tree, if you will. And then you have a field of A, which can be an animal. Currently it's not limited, but we can limit it a little bit and make an upper type bound. And we have a function called get, which returns this particular animal from the field. And then there is a function called large enough, which takes an argument of a field of mammal, and then returns false. And then you have a test function which takes a zebra field. So this constructs a zebra field, and in get you just return a new instance, and is large enough is implemented by is just called with zebra field. And now the idea is, does this work? And actually it doesn't, because the default case is invariance. So the Scala compiler tells you that there is a type mismatch here. It finds a field of zebra and is requiring a field of mammal. And because the type parameter in field is not set as covariant, contravariant, or invariant, it's like implicitly set to invariant. This is an actual type mismatch, because there's no subtyping relationship between these field types. And what you can do is you can make the type parameter covariant using this plus operator here in front of the type A. And this actually fixes the problem. And covariance, just to find another example that might lead you to see why contravariance might also be seen. Covariance typically people get. And let's say we have a class called vet, so veterinarian, and there is a function called treat, which treats all kinds of animals, and a function called treat mammals, which takes a vet for mammals and does something with it. And then we have a new vet for animals, and then treat animals, and then treat mammals with the same vet. And this, of course, is also a type match, because vet animal and vet mammal do not match because it's invariant. You've guessed that already. And what we can do is we can make a contravariant fix to the problem and say, okay, we accept any kind of veterinarian here as long as it's contravariant. And you might ask, okay, why do we need to have bounds and variance in our language? And when we inspect it a little bit closer, so say you have a collection you have a collection where A is a subclass of B. So A is the parameter in this case, and B is kind of the bound. So the collection takes any element from any class A, which is a subclass of B. And B plus gives you the same thing. It says, okay, it takes any element from any class A, which is also a subclass of B, but it also puts the collection itself into the subtyping relationship. With bounds, we don't have that. With bounds, we just kind of limit what we can use this collection for. With variance arguments, with the plus operator, for instance, or the minus operator, we don't make any limitation options, but we put the collection type in this case into a relationship, into a subtyping relationship with other collection types of other types, depending on their subtyping relationship. So we're linking them in a way. Now this is the difference between those two. And this is only useful when you want, in this case, collections to behave as the same way as their elements. Word of warning, don't overuse this feature. Sometimes this can be a little bit surprising. This is only useful when you explicitly want that. That's why you have to really turn it on if you want that behavior to happen. Sometimes you do, and sometimes you just don't. Okay. One nice thing that you can have in Scala, you can have not only type parameters, you can also have abstract type members. And this means that you can have member variables which represent types. So in this case, let's walk you through the code a little bit. So we have a trait called pet, and we have a class cat that extends this trait pet. And then we have a person, and that has a type parameter called pet. I could use it as a type parameter up there, but I here used it as a member variable, which has the nice thing that when we extend person, in this case with this class Susan, we can set pet to cat. And then we limited the type parameter much lower than we had before. Before it was open, and now we limited it. Like for Susan, this type means cat. So it means you can define a type, but leave it abstract until you know what it will be. And you can apply bounds here, and so on and so on and so on. This is pretty rich. But you can, the nice thing is you can leave it abstract and open until you know what it will be, specifically for a specific subclass of that class person. You can also do this with parameterized types, but it's a little bit easier to do this and it's less chatty. And the nice thing is you can have multiple members much easier than you will have to denote this in the syntax above. Technically, it is a rather similar feature. It does not have many differences, but it's sometimes a little bit easier to read in this way, to write it as an abstract type member. So in essence, we get abstraction without verbose type parameters, and this is pretty neat. So we can do abstraction, but we do not need to use verbose type parameters with lengthy parentheses and so on. We can just write type and then we're good. One nice and very overlooked feature in Scala 2, and this will be like superseded a little bit in Scala 3, but with a more general concept, but it's already in Scala 2. It's called existential types. And the idea here is that you can express some type-safe terms, even though you are still some parts are still unknown. So you have type safety, but with a few unknowns. No? So in this case, we have a case class called fruit, which has a type parameter t, and this type parameter is used in a value, which is basically a function. In this case, going from t to boolean to check if the class is too ripe. As you can see, it's a case class, so you can match and whatever to this. Is pretty neat. And then you have a form, which has a value called fruit, which is an array buffer of fruit of t for some type t. If you instantiate at that point, you otherwise would have to define what t now is. Here you can just say, okay, this is good for some type t. No? And the shorthand for this is the underscore operator. You've seen this, might have seen this actually already. The nice thing in the lang form is you can apply all sorts of bounds. So you can again bind the types, bind the possible assignable types at this point much easier, and institute a few bounds in that. And in essence, this is really helpful because it helps you to decouple implementation details from types. So you don't need to make your subclassing structure represent something that you would do in Java, because you need to kind of fan out into every simple direction. You can decouple these things and leave it open at these parts that are very general, and implement it at the parts that are then special for this particular case. So in this case, the toRipe function. You can delay that implementation until the very last point where you really need to tell how this is implemented. Quite neat feature. Yeah. Just a word. We use traits a lot, and the thing with traits is they need to be kind of linearized. At some point, because we have mixing composition, we can have multiple traits mixing in together. And there is a little example here. So we have this trait A, which defines like a common A, and then we have a trait B, which overrides A, which overrides this common again, and we have a trait C, which overrides this common again. And then we have two classes, D1, which extends B with C, and D2, which extends C with B. Trying this a little bit out in the console right now, so just that you see this. So we have trait A, def common is A. So we have a trait A defined, and then we have a trait B, which extends A and overrides common with B. Oops, this parenthesis. No. Come on, keyboard. There we go. And then we have trait C, which extends A and override def common C. Oops. There we go. And then we have class D1, which extends, what was the order again? B with C. B with C. And then we have class D2, which extends C with B. So what do you think is now this thing? Okay, D1 is not found. I have to find new D1, of course, and then call com. Yes. Let's see. and that's B. So the linearization gives you an order to which these overrides will happen, because they both override common. But the thing is, what happens here? And as you can see, D2 extends C with B, so the last thing is basically given. Okay, well, I have it actually here, so I didn't need to show you on the console, but I did nevertheless. Good. So here you see that the order in which you use these traits inside of the extends clause actually have a meaning. It defines the order of overriding. And with this, you can really make useful things. If you go back to the labs, you will see that the syntax parts are mixed in using traits. In the last labs also, I used traits a lot of things to mix in the certain features of the lambda calculus, the extensions that we did. And the order of things matters here a lot. And if you get that wrong, the outcome of that will be different than from your expectation. Okay, more complex thing is self-recursive or so-called f-bounded types. As you can see, when we go into recursion, things got complicated at any point. Not wrong here in this sense. So self-recursive here means that a subtype constraint is parameterized by one of the binders occurring on the left-hand side. So what does that mean? So let's say we have here fruits, and we have a compared to function which takes another fruit and then returns a boolean of true. And then we have apples and oranges that extend fruit, and then we instantiate a new apple and a new orange, and we don't want to compare apples to oranges, haha. And we don't want this to compile, because we only want to compare fruit to the same fruit. No, it did not. Interesting. I did not share an example here for this. Okay, I may have to give you that in Panda as well. However, you can basically do an f-bounded type here and say, okay, you can only compare things to each other, and then which is the exact type that we have given it and nothing else. Otherwise, you would compare apples to oranges, and that wouldn't be good. I don't know why there is no full solution here on this slide. Maybe someone deleted it. Strange. Maybe that someone was me. I don't know. I have to check and get back to you. Sorry for that. Okay, so going back to our last lecture, we have higher kind of types also in Scala. And the thing with traits and type parameters, or classes and type parameters, is that they're actually type constructors. So this definition here for a Q trait is actually a type constructor. Why is that the case? Let me show you. Why is that actually the case? So we don't need the exact methods, so I'm parameterizing a little bit. So let's say we have this trait myQ, and then what I can always do is to use this type parameter with another type and say not found. Okay, I need something like this, and use myQ with boolean. Oh, it's abstract. I cannot instantiate. Okay, I need. There we go. And then we have constructed a new type called myQ boolean. And as you can see, with our definition from last time, for type constructors, this is the exact definition. So I have a type constructor called myQ of t. It can be something like vector t, ref t. You get the picture. And then it constructs new types from this type constructor. And if I had methods in there, it would actually like create then the methods exactly for these types that I give it. So this is considered a type constructor. And we can actually look this up a little bit. So there is also a way to look up the kind of an actual thing here. So let's look at myQ a little bit. And myQ is an f of a. And if I turn on the verbose option a little bit, it gives us, aha, this is a type constructor, a first order kind of type. And this is the actual syntax that we've seen in the last lecture already. It's this star, arrow, star syntax that we have already seen in the last lecture. So Scala knows about what a type constructor is, and it is already telling us it's a first order kind of type. This also tells us Scala might also know about higher order kind of types. So let's look at this slide again. So we have another trait here called builder, which takes a type parameter, and here it takes a type member, which is basically the same. So let's say I would do the same in my console here again. So is this a higher kind of type? So let's construct something like this. Yeah, well, how do we call this? Not myQ, but myQ container maybe? I don't know. And this thing is depending on myQ, Q of underscore. We leave that open. We don't want to specify that particularly. It accepts it. So let's look what the kind of this is. And as you can see, it's star or a star equals a star. It's a type constructor that takes a type constructor. So a higher kind of type. And Scala has its own way of expressing it a little bit. It's XFA. This is a little bit of a shorthand for the same thing that we have here. So we don't use these stars. We have like variables that we can actually bind to something. It's actually what's been doing in the background. Let's look at this type a little bit more. So what kind of type is myQ container? What? We don't have a type called myQ container. Because we would need to specify it like this. Oops, no. I need an expression, sorry for that. How do we do that? Let's do new. Let's write it out. Let's say, okay, we have a Q container of myQ of Boolean. So what's this kind of type? No type parameters. myQ. Oh, that's abstract. myQ Boolean does not take any type parameters. What? Like this? Oh, interestingly, you can do it like this. Oh, interesting. And as you can see, it's a much more complex type. It has a single type thing and so on and so on. There is a whole bunch of stuff going on to address these higher order, higher kind of types here. Okay, let's move back to the slides. These two ways of defining higher kind of types in Scala are just the same thing as we discussed before between the things between type parameters and type members. This duality here is also reflected here. But as you can see, you can do higher kind of types in Scala. And interestingly, this slide again. Oh, well, is this the solution for that? No. It just plopped in the middle here for some reason. Oh, this is actually the solution for the solution slide that I mentioned for you. Sorry for my confusion here. Okay, let's then look at this a little bit. So I think the other slide just made it in between. This is weird. So as you can see, this trait did not have any type parameter here. However, we can limit it and say, okay, we can explicitly make it like this, and this fruit needs to be of type T, which is a subtype of fruit of T. And by this we have like self-recursive types. We now have this recursion in it. We then can use the type parameter in this comparator operation and then bind it to the same structure as we had before. So you can only then compare to your subtypes actually in this case, and then you don't compare apples and oranges because they both extend directly from fruit and don't have an intermediary that groups them together. So you then can make groups of apples and groups of oranges that you may compare to each other, but not apples and oranges because they're from the same, not from the same tree here. Good. Sorry for that mix-up. That was weird. One thing that you can have in Scala as well is structural types. You can define types on the fly by just forcing certain members. So what's done here is there is a function called close quietly, which takes a closable, and this closable is typed as something that has a function def close unit, nothing more. So there is no name for that. You don't need to define a new trait or class for that. You can just do it on the fly and just force, okay, anything that goes in here at least has a method called close that I can call. And then it actually does that and says try closable close, and then catches exceptions if they happen and ignores them. So close quietly. This is pretty neat because then all of them do not need to be in an explicit subtyping relationship. So you just introduce a new type that might be compatible to the things you want to. This is pretty neat, especially if you have like a helper method and that just calls one function and you don't want to introduce a whole inheritance structure for all of that. Then you can just use structural types and say, okay, I just need this close method to be defined as this, and don't bother about in which inheritance structure that is. So this is pretty neat because the compiler actually builds you the inheritance structure to make it compatible on the fly, which is so neat. So this means that this method close quietly can be applied to any type with a close method of the signature. And this is really, really neat. You can also do type aliases for that. So you can also define things like type members like this, opener closer, and then you have like two methods that go in there. And then say you have a type function that takes an opener closer and a function that goes from opener closer to unit. And then you can just call it open fun with this operator with the opener closer thing, and then close it again. So this is pretty neat if you do want to make like totally incompatible things compatible for just a small portion of their functionality. It can be pretty helpful in some cases. Path-dependent types are a thing that typically people need to wrap their head around at least a couple of times with implementing before they really understand it. So we already grasped dependent types, and we're going to come into dependent types sooner or later, but path-dependent types are kind of in a way a subset of that. So how does it work? So let's say you have an outer class and which contains an inner class, and then you have an object that gives you an instance of outer, and then you see the inner class of that out.one object. Yeah. And you do the same with the second instance of outer. Yeah. And then you have then you define a path dependency, path dep, as outer.one.inner. And then type check OK says path dep1 is out.in, and if you compare this with if you want to assign something to that same type of out2.in, this will not work. Okay, let's use this a little bit in the Scala console. Okay, first define our classes that we need. So something like this. And then let's not do the object. I can do this directly here in the console. Let's say, okay, we get an out1, which is a new outer, and out1in is out new out1 dot inner. Because it's a class, I can call it like this. And then out2 is the new outer, like a new instance. As you can see, these hash values differ. And then let's see, okay, we also do an instance of this other class. And then as you can see, outer, dollar, inner, and like two different objects. That's fine. But then let's see, okay, we have a new type, path dependency of out1.inner. And this is a new type. And then let's see, okay, we have a new val that says type check OK, and which is of this path dependent type. And we say we assign out1.in, in this case, oh, path, this wouldn't work, path. Path dependency 1, and this type checks really well. And let's take a new value called path check fails that is also of this path dependency 1, but we assign it this other object out2 in, and this actually checks because it's fails in this case because there's a type mismatch. So you found out2.inner but required path dep, which expands to out1.inner. So the type system actually differentiates types by their path. So if you have classes within classes, they are not compatible with each other unless they're from the same object. Why is this helpful? Well, if you want to make type hierarchies that are depending on certain runtime variables, this is pretty neat because then you don't mix things that shouldn't be mixed. Because the type system actually tells you, okay, well, this comes from a different path. So you have a little bit of a type depending on an expression. In this case, it's kind of the base object here, the out1 or the out2. It's not the full length of dependent types, though, I have to say, but you can do much similar things with them. Something, this is actually a behavior that is surprising to many programmers. So we use it sparingly, but it can be really used to differentiate different universes of different parts of your program pretty neatly out. And you can really separate things that actually the type checker is able to check if they mix and if they don't mix, if they stem from the original thing. For instance, if your base object here is kind of a frame of reference, something like a coordinate system, and then you have inner types representing things like a point or a square and so on, and then you really know that a point in one coordinate system is not a point in the other coordinate system, although they are both called point. And this can be really helpful in many cases to differentiate different universes in your programs. Get back to the slides. We've seen that. Intersection types. Now we're moving into Scala 3 a little bit. This is something that we haven't have so far in Scala 2, but like maybe in a mapping or a different extent. But in Scala 3, that's really unified. So intersection types allow you to combine different types together. And here you see that you have a trait resettable and a trait growable, and then you have a function that says, okay, you need to be resettable and growable, and all the other things I don't care about, but this is the things I depend on. And then you can assign anything that at least implements these two traits, because it needs to be able to reset and to add things also in this case. That's pretty neat. So X is required to be a resettable and a growable of string. So you can use type parameters and intersection types and plug it all together a little bit in this case. Union types are kind of the opposite. They give you a union of two things and say it needs to be either one or the other. It's a little bit like the either types that we discussed before, but you can like plug many of them together. And then you can make something like a help function in this case that takes usernames, passwords, whatever, and then you can use a match structure to then again differentiate your behavior for these different types. Again, you can do this with case classes and whatever or not. It's a little bit less elegant to do this with an inheritance structure. Because you have all these overheads to take care of, and sometimes you don't want to mix inheritance structures. And in this case, you can mix it in the parameter types, but not in the actual structure itself. So you can make an exception to the rule and things like that. So union types really helpful. So in this case, are they actually in here in my 2.13 console, I wonder. So let's say, oh, that's too much actually to type in, but let's walk through this a little bit. So let's say we have a password 123 and we have a username called Eve, and then if true, then we can let's just do this. Make it a little bit more easier. Make a case class username, name, string, so two different things, so totally separate. And then I say, okay, if true, password 123, else username band. By the way, that's not my password. And then you see a type mismatch here. So in this version of Scala, it says here, okay, sorry, that is actually me. I defined it as a string. Aha, and then we have a product type. So this is product with Java IO serializable. Well, not very informative. In Scala 3, this is actually something like this, object and product. Equals username Eve. Interesting. Do we have either types like this? I don't think we have them yet. Yeah, this is a Scala 3 example. Yeah. And there you can see, like, if we do this explicitly in Scala 3, we can get a much more narrow type for this, this password or username type. So this is a super type of username and product. And this is the least super type of username and product. Password. Typo. Sorry for that. Okay, as I mentioned, Scala 2 is the current version, but we are in the last 8 years, they developed hard on the next thing called Scala 3, or DOTI, which is the compiler, to a formalization called DOT, which is dependent object types. And this is coming out of EPFL in Lausanne, of course, where Scala was invented, and they are kind of the foundational parents of this language, and so they still advance it on the theoretical level. And this trickles basically good down into the practical parts of the language. They have a good system for that. And DOT has a very interesting thing. So this is the formalization of DOT from Nada Amin's doctoral thesis. By the way, really nice person. I met Nada once. As you can see, this looks already pretty familiar for this. I'm not showing you this so you can memorize this all by heart. I'm showing you this to see, okay, after this course now, you're able to read current science, at least to some degree. And as you can see, we have things like variables and type labels and method labels. Method labels may seem a little bit new, but we have contexts, and the operators and contexts you know pretty well. So we have an empty context, and you can add types to the context and then build your context. So you're pretty much aware of that. And then we have type variables. They define st and u because they need actually 3 things in there, which means that you have a bottom type and a top type. As we've seen in the Scala types system, this is the case here. And you have type members which have a lower and an upper bound, s and u. And this is interesting because they're not like exact, but you can have them defined in ranges. And this is actually what happens when you use type bounds. You define a lower and an upper range. You have an implicit lower and an upper range bound that define your types. And the type checker is then able to match it in that particular thing. And then you have method members, which have this neat little structure. I will come to what u to the power of x means, basically, in this case. Type selection. This is what we've seen now in path-dependent types. You have this recursive self-type. We've also seen this in code. And intersection and union types. And one thing, why with all the features that we had in Java 2, Scala 2, we need intersection and union types. And I can show you with a very interesting example that's actually from Nada herself. And the thing works a little bit like this. So let's import some structures from Scala itself. And the way that I do this is I say, okay, import Scala collection mutable. And I want to have 2 things important. First of all, the map. And I'm inside of the import, I'm renaming this type so I know it's mutable to mutable map. and set to mutable set. So it's just a rename. It's nothing more that I do here. I can do this in the Scala syntax. It's pretty neat. So I can have type aliases and so on. It's pretty cool. So I import these. And then I define an empty. Why is this console window jumping all of the time? I'm not doing anything. It's because it goes into and out of focus. Okay. And then I define a value with this mutable map. And in this mutable map, I store integers as the keys and mutable sets of integers as their members. And I initialize this just with the empty map. Great. So I have a Scala collection mutable map of int of Scala collection mutable set of int. Okay, this is fine. And then I define an if and say like, okay, if this ms contains 1. No, this is the condition. Mutable set plus 1 plus equals 1 to mapped to, this is the 1, m set 1. So this is how I add something to a map in Scala, by the way, by just defining that key value pair in this direction. And then the else branch of this is memory set of 1. Just look it up and do 1. And the interesting thing about this is it now tries to find a least common supertype for these two branches. And as you can see, it takes a while and produces this little neat type for that. And as you can see, this is an iterable with the type parameter with an upper bound of, and it actually doesn't stop. And people noticed this in Scala because compilation was going so slow that they asked themselves what happens there. And the reason for that is the Scala compiler or the type system was trying to find a join for these two paths and could only construct a very, very complex one. And as you can see, it goes into very little details here of whatever and this and clearable and with union and intersection types, you could just take the union respective the intersection, depending on the usage context, of these two types that we can like really closely define and have a much more narrow type to match it with. And this is what really makes intersection and union types so powerful in this context. Good. Coming back to theory. Unions and intersection types we just seen. They also look like joins and meets, by the way, because basically they are. But on the type level, so not implicitly. And then what do you have? You have variable references, you have new instance, and you have method invocation. By the way, this is the dot calculus without stores. I wanted to keep it a little bit more simple here. And then you have initialization, so you can initialize types, and you have like method initializations. Nothing fancy syntactic wise. Not giving you the semantics, but jumping right into typing. So the thing is, I'm walking you through this a little bit to see that you can actually understand this. It's not so rocket science with all the knowledge you just gained. And of course you have a var rule, as you have like in every language, but you also have this var pack rule, which is very helpful for function types as well. So you can pack function types in certain other types as well, and unpack these. So you can name function types a little bit better. Also helps. That's actually, sorry. Oh yeah, that's for self. That's the F bounded structure. I'm sorry, I explained that wrong. This is actually what you need for this f bound that we had with the fruits and the compare with apples and oranges. This is what enables you to do this, because it packs and unpacks these type parameters. Okay, subtyping in Scala 3 or in Dot, actually in the calculus, works a little bit like this. So you have a bottom and a top type, and as you know, there are like the subtype and the supertype of everything in your type system. And what you have there is like the rules for union and intersection types with ands and ors. And as you can see, you can leave things out in the end, or you can add things on the supertype level with the or type. And these things bind kind of together and say give you the subtyping structures for union and intersection types, so you can use them pretty much synonymously in as like value types in parameters where you actually want them to be used. Transitivity, always cool in subtyping that things are transitive. You also have that here. As you can see, not so much from the things you know. Pretty straightforward thing. You just have a T2 in between of T1 and T3. You've seen this a lot. Type and method members. The syntax here is a little bit simpler because you only have like top level methods. It's linearized and so on. It's a little bit of a neat trick to make things a little bit more easy on the proof level and on the rule level. But as you can see, you have like types which have like lower and upper bounds, and these lower and upper bounds correspond in the subtyping relationship. And as you can see, they are covariant and contravariant, just as the arrow type that you're used to. And the mechanics is basically the same. Same holds for functions here, as you can see. Same covariance and contravariance with the parameters and the return types again happening here as well. Remember that x in the power gives you the possibility to actually be self-recursive in the type again. You don't need to use it, but it actually is in there. Subsumption rule, also pretty neat. So if you have a subtype, you can always go. If you have something that is of a subtype, you can always use the supertype of that thing. So this is the subsumption rule that helps you basically construct supertypes if you need that too. But this is like the subsumption rules you already know. Good. And then you have like application rules. Application rules here are method invocation. And as you can see, they just bind the parameters together. This is nothing really fancy. This is just binding them together and saying, okay, now T contains this method. This gives you the power of structural typing that we just discussed, so that T is at least of this type that it contains this method when we see a method invocation. This forces it up the tree, and in the inference level, it just forces you to have types that have this method whenever you use this method. Makes sense. Yeah, and the TAP rule basically just binds and tells you, okay, this is then the outcome is the output parameter. Object creation, pretty neat thing. This is just saying, okay, whenever you create an object, when you have disjoint labels, of course, you create them from the template of the type. This is mechanics. I don't want to go into the details of this here much more. It's not really helping you understand. But as you can see, it's not like totally weird of a rule. Member initialization, type members. Type members, when you initialize them, lower and upper bounds of that particular type are the same. Whenever there is a subtyping relationship, and you see reflexivity here going on between T and T, so it's an easy thing to actually do. So this helps you to initialize type members. The defun is the definition of a function. So m of x is equals t, has the type of mx, t1 and t2, as long as t has the type t2 and x has the type t1. This is basically like an abstraction rule in the lambda calculus. It has the same mechanics. Path selection, there we go for path-dependent types. This is the rules for them. You have that path are subtypes of itself. This cell X rule here. And then you have the cell 1 and cell 2 rule that basically bind them in the upper or the lower bound where you have selection. Self-recursive types, this then binds this self-recursion. So you can actually have things like the fruit example where the type at that point in time is actually the type you expect in the parameter as well. This was this fruit t parameter thing that we had before. Okay, this is it basically for today. I've given you hopefully a good insight into Scala's type system and the theoretical foundations that are laying the ground for the new part of Scala 3. There is actually a core calculus for Scala 2 as well that has been evolved over time. It's been superseded now with dependent object types for Scala 3. However, there's work still going on, so read it up a little bit if you got interested, and you can actually do a lot more of practical examples with things like existential types, for instance. I will post you a few talks on that into Paul in the next weeks, so you can see that. Of course, like all the practical things, this is not part of any exams, or any kind of YouTube videos that I post are not part of the exam. What I told you today can be part of an exam, of course. But again, there's no point in memorizing all the rules. It's understanding them. That's the key point. Okay. Yeah, if you want to really look it up, so Nada's doctoral thesis is quite a good read. It's also not very long, so it's just 130 pages or so, I think. This is small for a doctoral thesis. Nevertheless, it's a very good thesis, so it didn't need to be longer, but it reads really easily. There is a few talks out there on the topic as well. I will post you a few more. This is just the things I'd used for this talk, to compile this talk for you today. Yeah, so as you can see, the Scala type system is pretty powerful in letting you achieve like making it work for you. So you can basically let it check for you any constraints that you have on your data or on your functionality that you would like to impose. However, you need to encode it a little bit, but then you can use the standard type checker for your specific application needs for all of this, which is pretty nice in my opinion. Okay, for this it would be it. Are there any more questions for this lecture today? While you're thinking about questions, word on the exam. I will give you all the exam modalities today in a Panda post. It's going to be an oral exam. That's no surprise here, and it's like 40 minutes as a standard oral exam goes. It will be virtual, that's new, so probably over Big Blue Button, Skype, or whatever we can control very good. And you will be asked then to join for your exam, and there will be me asking questions, of course, and you hopefully giving answers or asking questions again. This is also possible, and then a member of our group that will take notes and provide second opinions, of course, as it's common with an oral exam. If you are used to the format in person, you will recognize it in the virtual format as well. It's not that different. Also, this has been the last lecture in the setting. The next 2 weeks I will make a short session explaining in the first week the solution for exercise 11 and the solution for exercise 12. This will be the 2 last exercises. On July 1st, the last lab number 7 will come out. Again, you have 2 weeks for that, and then the semester ends. Oral exam dates will be then after, like from the first day the semester ends until roughly end of August, I would say. I do have some vacation plans, so I need to take that into account. I don't see any questions for the lecture today. Good. So with this, I'd like to close for today. Wish you all the best in preparing for the lecture, finishing the 2 final labs, of course. I've seen already some solutions for lab number 6 inside the system, but be aware that you can resubmit at any time until the deadline, so you can check for yourself afterwards if this works or not. Okay, just at this point, been a pleasure giving this lecture to you. I would have preferred to give it in person, of course, as we all would like to have. It's a rather new experience doing it like this. I hope it worked for you. It was a little bit more work for me, but I hope it also worked for you. Okay, let's then I see you either in the afternoon at 2:30. I just had to push it a little bit ahead, to the back, because I got an urgent meeting at 2, or otherwise in next 2 Wednesdays for the exercises, and until the end of the semester, of course, for the office hour. Okay, thank you very much, and enjoy.